One thing that's very useful for de Moivre's theorem is proving trig identities, because it allows us to turn complex numbers, or the Mod-arg form turns complex numbers into trig, and then we can use de Moivre's theorem to come up with identities. So let's use, well, the first ones we saw, our double angle results, sine 2 theta and cos 2 theta. All we've got to do is say, well, we know that cos theta plus I sine theta squared would be cos 2 theta plus I sine 2 theta. If I expand the right hand side out, we get cos squared, 2i sine theta cos theta, I squared sine squared, which is of course minus sine squared. But also we know that the real part must equal the real part, and the imaginary part must equal the imaginary part. So therefore, cos 2 theta is cos squared minus sine squared, and sine 2 theta is 2 sine theta cos theta. So it's a very quick way of proving those particular trig identities. So let's do 3 theta then. Same idea. Let's expand out the cubic. So cos cubed, 3i sine theta cos squared, but then we get 3i squared, but I squared is -1, so we get minus 3 sine squared cos. Then we'd get I cubed, which would be minus I. So we have minus I sine cubed, and equate the real and imaginaries, and we have sine 3 theta. There's 3 sine theta cos squared minus sine cubed. If I wanted that just in terms of sine, so that it sort of matches up, the sine goes to sine, well then we can sub in 1 minus sine squared for cos squared, expand out, play with the algebra, and we come up with 3 sine theta minus 4 sine cubed. And cos 3 theta, similar thing, we get 4 cos cubed minus 3 cos. The other one they've asked us for is tan 3 theta. Well, tan 3 theta is of course sine 3 theta over cos 3 theta. The trick to this one is not to use the final line, but to use the first line. So for sine 3 theta, I'll go 3 sine theta cos squared minus sine cubed. And for cos 3 theta, I'll go cos cubed minus 3 sine squared cos. And now I can turn everything into tans. All I have to do is divide by cos of the highest power. And the highest power in this case is cubed. So if I divide everything by cos cubed, what ends up happening is, well, the 3 sine theta cos squared cancels with the cos cubed, leaving with sine on cos, tan. Sine cubed on cos cubed, tan cubed. Cos cubed on cos cubed, 1. And then we have minus 3 sine squared cos on cos cubed. That'll cancel to leave sine squared on cos squared, tan squared. And so we have our result for tan 3 theta. So if you get one like that, the trick is not to use the simplified version at the end, but use the very first one that you got from using de Moivre's theorem. Show that x is equal to cos pi on 9 is a solution. Well, if I want to show something as a solution, I'd substitute in and go, oh look, it's equal to 0. Problem is, pi on 9, what's that? 20 degrees. We don't have an exact value for 20 degrees. I suppose we could try and work one out. How are we going to get 20 from manipulating 60s and 30s and 45s? It's a bit hard. Okay, if I factorise and rewrite the 8x cubed minus 6x, I get 2 outside of 4x cubed minus 3x. Now if you have a look back at the ones we just proved, have a look at the cos pattern. Cos 3 theta is 4 cos cubed minus 3 cos. So if I let x equal cos theta, then I can turn that into a simple little trig equation and so on. Because we'll get 4 cos cubed minus 3 cos, which we now know is cos 3 theta. And I've just got cos 3 theta is a half. Okay, that'll give me an answer. Well, in the first quadrant it'll be pi on 3. In the next one will be the fourth quadrant, wouldn't it? Fourth quadrant will be 5 pi on 3. And then I'd be back into the first quadrant again, 7 pi on 3. I need 3 solutions because it's a cubic, and I know there's going to be 3 answers here. Divide everything by 3. I have pi on 9, 5 pi on 9, 7 pi on 9, but that's theta. Remember, we said x was the cosine of theta. We require 3 consecutive solutions. It's also important those solutions are unique. In this case they are, because the cos of pi on 9 is different to the cos of 5 pi on 9, is different to the cos of 7 pi on 9, so we're fine. So there's our three answers. Well, they said show that x equals pi on 9 is the solution, so I've got one of the solutions. So there it is, pi on 9. But if you did just simply substitute it in, you could still do it that way, but just not work out what cos pi on 9 is. Because when you substituted that in, you would have got 8 cos cubed pi on 9 minus 6 cos pi on 9. But similar thing, you could factorise and you'll get 4 cos cubed pi on 9 minus 3 cos pi on 9. And then you can say, oh, hang on, now I'll use the triple angle result and turn that into cos of 3 pi on 9, which is pi on 2. We know what cos pi on 2 is. So we could still substitute that in if we wanted to for that one. The reason I didn't is because of the next part of the question where I do need to know all the solutions. And we've got evaluate cos pi on 9 times cos 2 pi on 9 times cos 5 pi on 9. So we've just worked out that pi on 9, 5 pi on 9 and 7 pi on 9 are the roots of this equation. If I use product of the roots, I'm not going to get quite what they want, but I'm certainly going to get 3 cosine functions multiplied together. So I know cos pi on 9 times cos 5 pi on 9, that's 2 that I want, times cos 7 pi on 9 is 1/8. So how do I turn cos 7 pi on 9 into cos 2 pi on 9? That's where we have to have a bit of a think about it. 7 pi on 9, that would be in the second quadrant. It would be an acute angle, I've got to take it away from pi, of 2 pi on 9. So cos 7 pi on 9 is the negative of cos 2 pi on 9. So I could substitute that in and dividing both sides by -1, I get a result that we're looking for. Cos pi on 9, cos 2 pi on 9 times cos 5 pi on 9 would be -1/8. Okay, so z's our standard complex number with a modulus of 1. It wants us to work out these two expressions. Okay, so I know z to the power of n, using the Moivre's theorem, the angle or the argument will multiply by n, so n theta. Well, 1 on z to the n is z to the negative n. So I can still use the Moivre's theorem. And I'll get cos of negative n theta plus I sine of negative n theta. But then I'll use odd and even functions. Cosine's an even function, so it'll be the same as cos n theta. Sine's an odd function, and you get minus I sine of n theta. So in fact, we have ended up with conjugates. And that's because the modulus is 1, that works. So the reciprocal and the conjugate turn out to be the same when you've got a modulus of 1. How did I know the reciprocal and the conjugate's the same? Do you remember the quick way of finding the reciprocal? Conjugate on the modulus squared. So if the modulus is 1, then the conjugate is the same as the reciprocal. Okay. So now I can add those two expressions together. Well, if I add them together, the imaginary parts will cancel, and I get 2 cos n theta. If I subtract them, now the real parts will cancel, and I get 2i sine n. Now those two little formulas here, if you like, can be quoted, unless of course that's what they've asked you to show. But yeah, and you can use that in solving problems, that little relationship. All right, so if I'm going to express cos cubed theta now in terms of cos some multiple of theta, so sort of going back the other way. Before it was cos 3 theta, and we were writing it in terms of just cos thetas. But now we're saying, righto, well here we go. I now know that 2 cos theta cubed would be the same as z plus 1 on z cubed. Because using my formula here, I'm just saying the power is 1, so z plus 1 on z must be 2 cos theta. Expand that out, and there's 8 cos cubed, but the symmetry of Pascal's triangle when we're expanding out binomials becomes very useful now, because I can group the things with the same coefficients. And I get z cubed plus 1 on z cubed, which again is in this pattern that we want, and 3 lots of z plus 1 on z, also in this pattern. So I could rewrite that as 2 cos 3 theta plus 6 cos theta. We're trying to, all I'm going to do now is divide by 8, don't I? And then I've got what they've asked for. So we get a quarter cos 3 theta plus 3/4 cos theta. All right, so let's have a go at some of those.